Right, good morning. So first up we have David Morrison, who I'm hoping... Excellent, he's here, that's great. David is a chartered structural engineer with over 20 years experience. He has worked for small and large firms both in Wellington and London, where he designed a high-rise office building and worked on the London Olympics. David is director of Morrison Design, based in Wellington. He spends most of his spare time with his young family or tending to his beehives. Join us, David.
Thanks, Michelle. I also wanted to say thanks to Carl Ashby and to Michelle and the whole organising committee. Arranging a conference of this size is certainly a huge undertaking, and we really appreciate your mahi, your work in this. As Michelle said, I'm here to talk about the design of scaffolds. I enjoy designing scaffolds. They're unique. The design's usually fairly fast-paced, and there's a challenging structural design. Often, after I've been briefed on the design of a scaffold, I'm wondering how we're going to get this design to work. A few of the topics we're going to cover this morning are compliance of scaffolds. So how do we get compliance for these designs? I'm going to run through some project examples with a focus on redundancy and alternative load paths. I'm going to talk about continuous improvement, about the need to confirm the equipment and design assumptions. I'm going to talk about safety in building design and maintenance considerations, and I'll wrap up with a few final thoughts. In terms of compliance, the design of scaffolds usually falls outside the Building Act. Sometimes it comes inside, but it's usually outside. So WorkSafe New Zealand has a good practice guideline, and that provides information on loads we should be applying in terms of gravity and live loads. But it doesn't cover wind loads or earthquake. So for those loads, we need to be looking at 1170. And it's worth noting that 1170 is intended for buildings. So right from the outset, we're getting a standard that's not really intended for scaffolds, and we're applying that standard to scaffolds. So we certainly need to be using care and judgment with that. A lot of the trade literature and products for scaffolds are designed overseas. They're intended for the overseas markets. So we need to have care when we're applying these overseas products to the New Zealand situation. And often that will mean down-rating the published data for the products we're using in order to comply with the WorkSafe requirements. The first example we're going to look at is this office building refurbishment scaffold. The design for this one, the main contractor, they wanted to have the ability to remove the bottom sections of scaffold but have the top section still in place. And you can see they've already started putting the cladding on down the bottom, and they still have the scaffold up the top. So we are cantilevering out, and I don't know if you can see those needle beams coming through supporting the scaffold at the high level. This is a photo earlier on in the construction, and the bottom section of scaffold here is actually independently supported from the top section, so they can remove that bottom section and just leave that middle section in place. As you might imagine, the design of this sort of scaffold has a high consequence of failure. So we really need to be thinking about redundancy and alternative load paths with a scaffold like this. This is a drawing showing a section through the scaffold, and you can see we've got a cantilever beam that sits on the slab. We've fixed down through that bottom slab to prevent uplift at the back end of the cantilever. But in addition to that, we've installed a strut to the slab above. So if anything were to happen to that fixing to the bottom slab, we've got a secondary load path propping to the slab above. As well as that, sort of through this section, through that section through there, we've got diagonal members running within the scaffold depth, so that if for whatever reason something did happen to one of these cantilevers, load could be shared out to the adjacent cantilevers to prevent anything catastrophic. This is a photo of the underside of the slab where we've fixed through. You can see the waffle slab there, and we've grabbed hold of 3 of the ribs. We possibly could have just grabbed hold of 2, but we've got beams long enough to grab hold of 3, so why not? This is another project. It's a roof encapsulation project, and these are becoming more and more common for weather protection. It allows the building work to carry on almost independent of the weather conditions outside. This particular one is being installed because it's an asbestos roof that's being replaced. The truss system we've got here is a Keta truss, and it's designed in Europe for European conditions. So the way they've designed this is so that for snow load, it'll have a strong or strength in the downwards direction. However, down in windy Wellington, our main consideration is the wind uplift. So we're getting a product from overseas, and we're applying loads in the wrong direction for that product. The ends of these trusses, to stop it from taking to flight, we would usually attach to the building, either using mechanical anchors or chemical anchors, or sometimes we'll add concrete or water counterweights at both ends. You can see here in the photo, we've got a truck strop in blue there, and that's cutting down the effective length in the uplift condition for the scaffold. So it's fine for the downward, where it's got plenty of strength, but for the uplift, we've got those strops cutting down the span. Something we need to consider for a design of a scaffold like this is whether we're going to apply the 1170 CPI internal pressure wind factors or not. For a large volume, like you can see in this photo, we would typically apply those CPI factors. But if the scaffold were located quite close to the main structure and there wasn't really the ability to get those CPI factors, we may neglect them. But that's something that designers need to have care with and give consideration to. Another thing to think about is sometimes we get requests for the scaffold to be completely independent from the building and have no attachment to it. And this is something you need to be careful with those requests, because once the scaffold's no longer attached to the building, it sort of stops being a scaffold and it becomes a building in its own. So all the load considerations and all the calculations and design elements you might do for a normal building, you then have to do for your scaffold. This project is a loading platform, and this photo is a view of the underside of that loading platform. Our client had a piece of fairly heavy machinery. It was about 7.5 tonnes, and they wanted to take the machinery down the platform and then move it into the building. This particular piece of equipment, once they unplugged it from one end and they started moving it to site, a clock started ticking, and if anything bad happened to the platform, you'd end up with a fairly expensive junked piece of equipment. So we met with the contractor several times to confirm the exact dimensions of the wheels on the equipment that they're going to be moving. And as you might imagine, the scaffold decks they've got here, they're not intended to support 7.5 tonne. They're sort of intended to support a painter, maybe a paint pail and a paintbrush. So we're getting a product and taking it well outside what it was intended use was. So what we've done through here is we've installed timber blocks between the scaffold deck and those soldier beams which are running in and out of this photo. And that transfers the load directly from the top of the deck. The deck doesn't really experience the force. Load goes directly into these soldier beams. As I mentioned, the exact location of the equipment is fairly important here. If it started to drift off to the left or drift off to the right, it could be fairly catastrophic and fairly expensive mistake. This project is an access scaffold to carry out maintenance on a church spire. And the funny thing about church spires is they're often attached to church buildings. And that poses a problem when we're trying to build a scaffold up because the roof gets in the way. So the contractor popped a hole through the roof for us and provided one point of support. And then we used the scaffold itself as a truss system to span onto that point of support. Usually, when we have a scaffold, we consider the building to be the rigid element and the scaffold to be the more flexible, so we're transferring load out of the scaffold and into the building. This project certainly challenged that assumption. Towards the top of the timber spire, there's certainly a lot of deflection in the wind case. So it turned out that our scaffold was certainly more stiff than the top of the spire. The contractor had a request to install a cloth scrim around the top of the scaffold. However, the wind loads were going to be too much for that. The spire wouldn't support it, and the scaffold wouldn't either. So instead of having that cloth scrim to catch any equipment which might accidentally fall off the scaffold, a catch fan was installed to the lower section of the scaffold. The catch fan was put out every day that they were going to be working on the top section of scaffold, and then each night after they'd finished their work, they brought the catch fan back in. So tying in with the theme of looking back in order to look forward, I'm going to touch on some continuous improvement and talk about construction sequencing. This was particularly highlighted to me how far we'd moved on because we've scaffolded the same building 3 times in the last 5 years. This building in Wellington is a fairly typical with a low-rise podium, and then the building carries on up with a tower. And what we usually do for a building like this is we would attach brackets onto the columns, as you can see in the photo here. We have something spanning between those brackets, and then we build up with a scaffold off that. The brackets are usually attached to the building either with mechanical or chemical anchors. In this photo you can see that we have an aluminium truss that's spanning between those brackets. And the aluminium truss system isn't necessarily bad, but it does have a high reliance on friction couplers, the scaffold friction couplers. In this photo you can see the loads coming down the scaffold legs, and it accumulates to some fairly big reactions at those column locations. In this photo here, it's a zoomed in view. You can see that at the point where we've got these brackets, there's only 2 of these friction couplers which are taking the whole load of the bay span between the columns. And while we can get the numbers to work for this, we did it slightly differently in 2019 when we did the building again. By this stage, our client had bought several container loads of these steel soldier beams. You can see that we're spanning between columns here. And the real advantage of this system is that instead of relying on friction couplers to transfer all our load, the scaffold legs are able to land directly on top of the soldier. So we're not relying on those friction couplers. So this has got a lot more redundancy in it. And it's not much extra effort, and it was just a switch out from one product to another. This is what the building looks like in 2021. We're scaffolding it. You can see this area in the middle, they're now doing work at the top of the building, so we've sort of omitted a whole lot of scaffold equipment down the bottom. I wanted to quickly chat about the importance of communicating with the contractors regarding the dismantle and construction of the scaffold. This is a CAD version of the photo we've just seen. Where we're using the scaffold itself as a truss system to span between these brackets, usually the builders, they would build the scaffold at the bottom and then they work their way up. Often when they're dismantling, or usually they'd start at the top and work their way down. Sometimes the scaffolders will request that they can dismantle from left to right or right to left, and that can cause instability if we're relying on the scaffold itself as a truss. You may have some situations where you've essentially eroded half of that truss that's spanning between the brackets. So it's worth confirming with the scaffold firm their dismantle sequence particularly, and their construction sequence that they're intending to use. This is a different building in Wellington, some of you might recognise, and with this building I wanted to just talk about the importance of confirming your design assumptions, getting hold of proper documentation for the building, and going to visit the building is really important. At first glance, we might think this is similar to the previous building we're looking at, podium and tower. We'll chuck some brackets on the columns, span between them, and off we go. But when we went and inspected the building, we found that actually this is just a precast facade. The main structure is set back quite a bit from this facade, so attaching brackets to this wasn't going to work out, and we ended up going with a different methodology for our design. I want to have a quick chat about safety and building design and maintenance considerations for our buildings. This is the same building from the previous slide, and while they were carrying out the maintenance work for the building, they also wanted to replace some mechanical plant up in the, which is located up the top of the building. So in order to do that, they've removed some facade panels from the building, and they're going to crane in some equipment, but they can't just crane the equipment directly into the building. So they needed a platform to land that on, and then they're going to push the equipment into the building after that. And it sounds easy enough if you're sitting in a design office to say, yeah, we're going to have a platform, and in it goes. But certainly the construction of a platform like that, that's going to hold several tonne of load that high up a building, is a lot easier said than done. We've got guys with fall arrest systems. There's big safety from falling from height risks. And as building designers, we really need to be thinking about how we can mitigate this risk of having people working, carrying out this sort of high-risk construction work. You can see we've had to install some soldier beams up. This is the same platform. We've had to put chemical anchors into the building, so we've had guys on harnesses installing those chemical anchors. Big beams spanning between these trusses we've got coming off the building. It was quite an undertaking. Something else we need to be thinking about as building designers is the signage for the buildings we're doing. As structural engineers, we're usually thinking about beams and columns and floors maybe. But as we're sitting around the design table with our architects and building owners, it's worth giving some thought to the signage. The naming rights for a building will probably change hands several times during the building's life. So at some stage, someone's going to have to get up there, take the sign off and put a new one on. For this particular building, we had a couple of options. Ideally, we would have started at the ground and built a scaffold up, and then they would have done the signage that way. But you can see there's a fairly large canopy down at bottom level, which prevented that. So our other option was to cantilever off the roof and put the signage in that way. You can see that this is quite an undertaking to do these cantilever scaffolds. The building just had a brand new membrane roof on it, so they certainly didn't want us drilling through that and installing anchors. So we've installed anchors where we can and a series of counterweights, but it's quite an undertaking. And as building designers, I think we sort of owe it to our clients and to construction personnel to try and avoid these sorts of situations. This building's, I don't mean to pick on this particular building, we've done the similar things for lots of different buildings in Wellington. I'm just going to wrap up with a few final thoughts. This morning we've talked about a few different types of scaffolds and the different design issues associated with those different scaffolds. I enjoy the design of scaffolds. It's fast-paced, but we need, as designers, if we're going to be designing scaffolds, we need to have our wits about us. We need to be thinking about the products we're using, not just taking the trade literature at face value. We need to be digging in, seeing the data behind those, and making sure that the products we're using are appropriate for the New Zealand situation. We need to be thinking about the consequence of failure of our scaffolds and the need for redundancy in our design and alternative load paths. And as building designers, we really need to be thinking about how we can avoid the need for these high-risk scaffolds and consider the long-term maintenance of our buildings. So, thank you.
Thank you, David. Tripping over. We have time for one question, I think. Oh, Gordon, we have someone.
In the design of scaffolding, what return period wind speed do you use?
Sorry, I thought I'd gotten off easy.
Just stay there.
It's a 1 in 100 year event. It doesn't give you a whole lot of down rating from the full building load. The justification from that is from 1170. So 1170 has a return period for scaffold and construction equipment. Yeah, it's likely to do, yeah.
Okay, well, you don't get off that easy. There's actually 2 minutes, so we've got another question if anyone has got another question.
It's similar, 1 in 100, yeah. We didn't. A lot of our high-rise scaffolds are shrink-wrapped and they're attached to the buildings. So really, wind load is the huge governing case for us. Given how lightweight they are. Yeah.
How do you deal with the design of the friction couplers? Is there empirical data that you use, or because it's not something I've done some scaffolding stuff before, and I generally just get them to put bolts in because I don't really trust them.
Yeah, there is published data for it. 6.25 kilonewton slip, I think, is the off the top of my head. Yeah, what they're good for. Yeah.
So is that sort of quite conservative, because doesn't it depend quite a lot on the installation?
It does depend a lot on the installation, and that has a factor of safety of 2 in it. But those friction couplers are intended for a right angle connection. If they don't have a perfect right angle, and if one of those is slightly skewed, then the coupler won't grab hold of the tube properly. And there have been examples of those slipping because of that. Yeah.
All right, well, join me in thanking David. If you have any more questions, I'm sure we can harangue him at lunch. So thank you, David.
Thank you.
Our next speaker, Mr. Ian Watson, if you want to join me. This morning I asked you all to welcome Ian. He's a sole practice structural and civil engineer to share with us his experiences around the awful topic of being sued. I'm looking forward to hearing what you have to say. Ian works alone from his small farm north of Auckland, but he does have friends. Heidi, a pet cow, and Max, a mad as a hatter rescue dog. His wife Sharon has tolerated him for 47 years, as have his 3 children, and he has 6 young grandkids to keep him on his toes. So welcome, Ian.
There we go. Just to prove the point, that's my cow Heidi. She's beautiful, isn't she? Here's Max. And here's my beautiful granddaughter Isla. 10 tips to help you from being sued. One Saturday in May 1995, I was at home with the family on a Saturday morning, and a car came down the driveway. A man in a suit stepped out and he said, "Mr. Watson?" I said, "Yes." And with that, he handed me a ream-sized bundle of papers. "You are hereby served notice of proceedings in court." And with that, he left. I felt horrible. I felt sick, physically sick. My heart was pounding. I was red in the face. And then I had to explain what had happened to my wife. Not an easy task. Over the coming days, I found it hard to sleep, lying in bed, going over the events that had led to this situation. Today, I want to share with you my own experiences working as a sole practitioner engineer and being taken to court on several occasions, as well as times when I had to work really hard to avoid a dispute or a failure. What lessons did I learn? How can we as practicing engineers best avoid the events and disputes that lead to court action? Oops. Lesson 1. In facing these challenges as a profession, we tend to concentrate on issues such as the importance of keeping good records, keeping up to date and having our calculations checked, i.e. good office procedures. But do we often think about how to avoid getting into a situation in the first place where we might get sued? For instance, through our relationships with others, other professionals. Let's say, for instance, you work in Auckland and you've got a house to design in Tauranga. And you need a geotech engineer in Tauranga. So you're referred to somebody. But how do you know that you can depend on that geotech engineer? If he makes a mistake, you are going to be drawn in to a legal dispute. We need to be able to work with trusted colleagues. With regard to the regular clients that you deal with, are they insured? And do they take their responsibility seriously? Their mistakes could draw you into a dispute of not your making. So lesson 1, choose your work colleagues carefully. Lesson 2, be aware of how the legal system works. I was involved in a case quite a few years ago where a large 2-storey office building developed leaks. I had carried out a peer review for the structural engineer. The developer claimed that the roof leaked because the roof beams sagged, which was not the case, of course, but I was drawn into a case anyway. In this case, I had to attend meetings, and finally we had another meeting in which everybody sat around the room and we agreed on an amount of money each party would give to the settlement. It was either that or go to court. In this case, there were tradesmen, plasterers, roofers, the builder, then the engineer, the architect, and of course the council. And all of them contributed to the case because the alternative would have been to go to a court and have a solicitor sitting next to you at $300 or $400 an hour. They quickly worked out that it was cheaper to settle. So you need to know that that's the way the system works. Very few cases go to court, so be prepared to negotiate in pre-court hearings. In this particular case, I was quite angry. I refused to contribute. And I would have been prepared to go to court because I knew that my insurance partner supported me, and in fact my legal costs would have been paid for me. So I had a strong negotiating position because of my insurance partner. Other people in the room were not so fortunate. They knew that it was either settle now or go to court at a huge cost. I feel very sorry for the tradesmen like plasterers and roofers who have no liability in this case really, but that because of the legal way the system works, they felt forced to cough up. Lesson 3. Choose your insurance partner carefully. In evaluating which insurance partners to select for your professional indemnity cover, make sure you compare the benefits of each organisation. Some insurance companies, partners like CEAS, will cover the cost of your legal fees, even whether you've heard or not. And they will give you good advice leading up to any settlement. Other companies may not have this provision to support you with legal costs. The annual premiums we pay for insurance are a significant cost, but you have to ask yourself, is it covering all the things that you require? For me, as a small practice engineer, having peace of mind in knowing that if a situation arose that needed advice from another engineer or a solicitor, I could get that advice from CEAS. And in fact, I unashamedly recommend CEAS, particularly to all small practices. So choose an organisation that's going to also to be around for the long haul. If they go bust, you could be left high and dry with a claim. I've personally seen engineers caught out in this way. So I unashamedly recommend CAS because it's run by New Zealand engineers and it will be around for the long haul. Lesson 4. Identify who takes responsibility for what. If you look at the claims notification records from CEAS, a large percentage are geotechnical related. That's just because New Zealand has difficult soils. So if you are designing a building and unknown soils, make sure you're getting good geotechnical advice. Make sure the documentation clearly states who's responsible for what, and insist that the geotech inspects the work, and you have clear documentations which delineate which work is covered by each party. Lesson 5. Identify work that's high risk for you in your practice. I call these red light projects. And the classic for me was a retaining wall on a boundary. 2 neighbours. So if something goes wrong, you immediately have 2 parties arguing as to who is to blame. Visit the site. See the contours. check for potential surcharges. I went to a job some time ago and the architect gave me the height of the wall. He'd been on site and he measured up to the fence line. When I got to the site to check the holes, I went around the other side of the fence and realised that somebody had raised the ground 300 millimetres and then put a concrete slab and parked their car there. So immediately, huge surcharges. Ensure the documentation requires that the contractor provides support for cut banks during construction. Foresee the problems and act accordingly. What are the high-risk projects for you? Lesson 6, we all know this one, don't work outside the level of your competency. As a young engineer working for myself, I had a go at many disciplines. I purchased equipment so I could drill holes to 3 metres deep, and soon I was producing soils reports. But on one job I was caught out. A reputable company had prepared a soils report which stated the site was stable from slips. My tests on the house site itself were okay, so the house was duly constructed. During Cyclone Bowler in 1988, the heavy rain caused many slips in Northland. And on this site, the whole 10 acres went on the move. The house was evacuated in the middle of the night by the police, and the house itself was a write-off. After that, I put away my soil testing equipment. The claim against me and the geotechnical engineer and the council was upheld, as you would expect. Lesson, don't exceed the level of your competence and experience. Lesson 7, keep your documentation and invoicing up to date and relevant. Craig mentioned this yesterday. Get your claims in for your final invoice quickly. The client might find some nebulous technical reason to withhold payment, and a PI claim can ensue. Have a carefully worded contract that excludes the work you're not engaged to do. Make sure your plans and calculations have similar exclusions. ENZ and CSOC have lots of information about the documentation you need to show. Discuss these with colleagues and share lessons. Keep up to date. Lesson 8. When something does go wrong, don't admit liability, but do everything you can to mitigate the fallout. Show the client that you're keen to rectify the situation without saying who is to blame. Often a client will be happy to fix the problem at their cost if they have your support. I used to think that not admitting liability meant that I shouldn't get involved in the remedial work, as this could be seen as admitting liability. But often the client just wants to get the problem fixed quickly so he can move on and complete the project. Lesson 9. Allow your work habits and knowledge to be scrutinised by your peers. Get a little bit vulnerable. Where I work in the Rodney area, we have a local group that meets once a month for a coffee. We have no agenda. We've been meeting like this for over 10 years. I believe there's another group here in Hamilton. So we mostly just grizzle about the Auckland Council. But it's been a great way to get to know other engineers who face the same challenges And I know that if I was to need help with a situation, there are other engineers around me who would provide that help. We need to be able to share our work issues with each other, rather than pretend that we know everything. I had the misconception in my early career that if I allowed my colleagues to know how little I knew about some things, they would judge me badly. As I opened up to others, I realised that they too had weaknesses, and in fact, I could assist them. It's really good for your mental health if you can get together and chat with other engineers. Lesson 9, allow yourself to open up with other engineers. Lesson 10, go easy on yourself. Each time I was involved in a problem, it was extremely stressful. And while I dealt with that problem, my other projects suffered. As a sole practitioner particularly, we carry that burden on our own. But we do work in a very high-risk industry with big projects and big risks. The chances are high that at some stage in your career, something is going to go a bit wrong. That's why we pay comprehensive insurance. So be a little easy on yourself and accept that it's not a disgrace to be drawn into a legal dispute. Mental health is now an issue being addressed in the workplace, and for engineers, the responsibility we carry is huge. You will have times when the stress is immense, and you will feel emotions such as failure, inadequacy, and perhaps fear. I often experienced these feelings when I found I'd made a design error and had to front up to the client about it. It was very hard, but generally people accept that we are human and we all make mistakes from time to time. It's just that in our case, the mistakes can have huge consequences. So go easy on yourself. In summary today, I would say, build your business on firm foundations. Select a reliable insurance partner. Look to dependable work colleagues. And have a sound knowledge about how the legal system works and how it impacts your work. Establish good work routines for your work patterns so that they're crisp and clear to you. And thirdly, manage yourself. Watch for stress signs and share with a few colleagues and have a coffee on a regular basis and share the burdens when they arise. And if the worst comes to the worst and you get caught in a case, know that many others of us have been there before you and understand how you're feeling. We do work in a high-risk business. Set up your business well, have good work routines, and allow yourself to open up to a few trusted colleagues along the way. Are there any questions?
Okay, so our next speaker is Martin Pratchett. Martin has been the Engineering Practice Manager at Engineering New Zealand since 2019. Before starting at Engineering New Zealand, he worked as an engineer for a structural engineering company in the Lower Hutt in Wellington. Martin has been great in developing messaging on some hot topics for all of us and driving initiatives around idea sharing, with some recent examples being the guide on residential portal frames and an article on remote construction monitoring. Thanks, Martin.
Thanks, Michelle. I don't have a crazy cow, but I'd quite like one. So when I first came to this job in 2019, it occurred that there was a real lack of feedback loops into engineering New Zealand, and that and they said to me, so what problems are you going to start working on? And I said, what problems are there? And actually nobody could tell me. So the way that I decided to do it was to reach out to some of the BCAs and say, what are some of the common problems that you guys are seeing? Managed to get some data from Auckland Council first of all and started to analyse that, and found out that was the trick of how do you use the button. There we are, magic. It's the blue one for future presenters. And found out that actually a lot of it is around the way that your documents are prepared and put in. It's this has actually been backed up by a recent project that I've just finished, which involved me doing a high-level review of engineers' work throughout New Zealand, mostly in the residential space, 1 and 2 story buildings, but also with your walk-up apartments and so on. And in some of those, I actually couldn't understand what the engineer had done. This was all consented work, by the way. And I thought to myself, I'm not the smartest engineer in the room, I consider myself fairly firmly in the average. But if I can't understand it as someone who has, worked as a structural engineer, then how can the council check us, and how can anybody else? And I then went back through the RFI records for some of those jobs, and they had repeated RFIs on them before they'd actually been consented. And I think that it had just eventually become death by RFI for some of them. But I kind of worked out, just from my own experience of working, and I thought, well, how long did it take for me to answer an RFI if I just made a silly mistake or had to answer a question that was there because I hadn't made something clear in my own documentation, right? And it was around about an hour, somewhere between about half an hour to an hour. So I rounded it up to an hour. So then how often does that happen? Well, maybe you get, an RFI that you've got to answer like that, and maybe it's only one question out of that every couple of weeks, But if you actually start to multiply that out, and let's say that we have a charge-out rate, for a couple of $100 an hour, and then you multiply that with one RFI that really could have been avoided every couple of weeks, and pretty soon you're looking over $5,000 a year. Now, in the engineering firm that I used to work for, we had about 12 to 15 engineers working there. And so pretty quickly, you're looking somewhere between $75,000 and $100,000 a year that you're losing just because of the documentation mistakes. Now, I actually, Alistair Fusel from Steel Construction New Zealand found out that I was going to be doing this presentation. He got in touch with me and he said, what are you looking at around the RFIs that people are getting during the construction stage on steelwork and so on? And I said, nothing, didn't occur to me. And so he said, can we sort of join forces on that one? And I'll provide you some data. I said, yeah, no, that's great. But as we can see here from the, yep, you can see that pretty well. So this fits pretty well with what the types of construction that we have in New Zealand are. It's around about 75 to 80% of construction that occurs in New Zealand is residential. That's the majority of the work that we do as engineers. And around about 20% of it is commercial. That's backed up by Brand's data. Now the documentation, as you can see here, producer statement issues, inadequate description of work, your construction monitoring, what are you going to be monitoring and who's going to be doing it was inadequate. Durability to a certain extent. And then are your assumptions reasonable, calculations and issues with the drawings, right? So these aren't, big things on the whole. It's just things that we should have been doing better. Now, I'd just like to say, work is always a learning experience. Please don't try and dig out some of my old jobs and look at that as a perfect example, because they're definitely not. But when I was down in Christchurch at the last President's Roadshow, you know, we sort of talked about some of these issues, and it was John Tate, actually, who came up and he said, well, what does good look like, you know? I mean, you submit work across different BCAs, and they all want different things, you know, in one part of the South Island, and they were fine just with a PS1, you know, and that was pretty well it. Whereas you try to get away with that in Auckland or Christchurch, you forget about that, you know. So what does good look like? And the thing is that different BCAs do want different things, you know, so we're going to have to figure out what is the common. But they all want it to be good, basically. And so typically in there you're going to need your PS1 for 80% of work, as we've discovered. You need your certificate of building work. B2 statement, particularly if you're using exposed steelwork. Stanley Chung, we heard yesterday, saying that, you know, design features report is really important. And actually, of the work that I saw when I was doing that review, very few of them had a design features report in there or any pictures, right? It makes it really hard to check other people's work if you don't have any pictures. Construction monitoring schedule. I saw very little evidence of construction monitoring schedules on the work that I was inspecting. And in there, you know, we need to make sure that people are aware of who's going to be inspecting the work that we're designing. The builders need to know when to call us. And if we're going to be doing something like bracing, for example, or, you know, maybe some timber lintels or whatever, and we're expecting the building consent officer to check that, then that's fine, you know. I mean, I don't think I've ever gone out and inspected the screw patterns on bracing. But we need to be stating that somewhere, that the building consent officer should be doing that. And some pictures of project and calculations in relevant sections with some pictures. So this is the data from Alistair from SCNZ. And what he did was he said, okay, so let's look at a couple of similar projects, a fairly simple portal frame warehouse. Project 1 was good with, you know, good documentation, and Project 2 was an example of poor documentation. And so what he did was he approached a fabricator and said, can I get the number of RFIs that you know, issued for these jobs? And then compared it. And so for number 1, they got 10 RFIs, right? And for the second one, they got 70. And so he said, well, how long does it take him, you know, who's very experienced at this type of work, to be able to answer those RFIs? And he said, it's around about half an hour for an RFI, right? And so once again, if we just use a basic charge out rate of a couple of $100 because it makes the maths easy, then all of a sudden you may have underbid on that job by, you know, $3,000, $4,000, whatever else it may be, but then you're having to answer all of those RFIs, and pretty quickly, you know, that money that you've undercut the competitor by is gone, you know, and actually you're losing money on it. And so this is where we're starting to look at some, you know, what should the design fees be for these things, and that's another conversation. And so something that I started to do is I thought, okay, well, let's get together a little bit of a package around what good does actually look like, right? And so on my commute, I tend to cycle past quite a few houses that obviously needed engineering work, and I just chose one at random, which was, you know, I knew had some work done in the last 10 years. Grabbed the calculations from the Hutt City Council website and anonymised them and reformatted them. Actually, the guy had done a really good job, which was great to see. And so what we need here, some of it, by the way, is a shameless plug for Engineering New Zealand documentation. And so the first thing, you know, you need your producer statement. One of the things that you commonly see in there is the design code clause, B1, you know. Please don't put B2. If you want to know why not, come to my next presentation. Don't sign for B2. You need to keep this stuff fairly brief. There's examples on how we do it, and Adam Thornton does a course on producer statements. The next ones are going to be launched in August 17th. So we do have an update for the producer statement series coming out. and there'll be a webinar that I'm doing again. One of the things that we have here is that sometimes for a simple beam, you can end up with a huge amount of documentation, right? I remember doing a job and literally it was one timber beam in a house with a point load on it. And it took me, I don't know, 10, 15 minutes to design the beam. It took me about an hour to fill out all the paperwork. And it just gets a little bit over the top sometimes, in my opinion. And so one of the things that I've done, which is being launched on August the 17th as well, is to start to integrate all of that paperwork so that when you go in and get the PS1 off of the Engineering New Zealand website, you'll just be able to click on a link and it'll come up and say, you want a design features report, construction monitoring report, this, that, everything else as well. And you'll be able to go in and fill it all out, and all the fields will auto-populate for, so you're not typing in duplicate information. And those are the forms that these forms are based on. If you've got questions about that, feel free to ask me during lunch break. And so this is our certificate of design work. We have changed the form from the MB one to simplify it and try to make it a little bit more fraud resistant. It turned out that Auckland Council said that there were some instances of fraud, so we've changed it into a 2-page document, which for the purposes of brevity I've put into a 1. And then your letter in lieu for design work. This is just downloadable off the Engineering New Zealand website as well, and is now commonly accepted through the BCAs. Design features report. Now, for most residential work, you're going to ask me a question? Oh, we'll wait until after the thing. With the design features report, CSOC have got a great one for commercial work. We've condensed this one down into a couple of pages, and there was a question during Stanley Chung's presentation yesterday about the blurb at the front, of the design features report, and could we do better? Yeah, probably, It's a good way of keeping it done. If we can be detailing out what our loads are and so on, then it makes it a lot easier to check. If you can be putting it down there, then with a picture, then you're likely to get a lot less questions from the checking engineer. The reason being that they can see at a glance what's going on. Are your assumptions right? And if your assumptions look about right, then chances are the rest of your documentation is going to flow through, right? It's also a really good way for you yourself to be able to look back at the job and say, actually, have I got this right? And we can sit here and we can say, actually, yeah, I do that. But having looked throughout the jobs from the country, then actually most of us don't. So, highly recommend it. And then put in a bit of a picture of the project. Picture tells 1,000 words, and so this is the house that I cycle past. And so, just looking at it, some of the things that we could say, okay, well, it's going to need, a bit of a frame at the front there, possibly a short, soft story, and it looks like you've got some block work and level ground and so on and so on and so on, lightweight roof, lightweight framing at the top. Straight away you can see this, and it doesn't take too much effort just to get a snip of the architecturals and put those in. Now, as we've seen from some recent work, I have deliberately kept this fairly rough, by the way, so that you can see that it's that it was some real work that somebody did. I haven't checked all the calculations or anything, by the way, so. But so from some of the work, the big projects that we've seen lately is structures not standing up under gravity, and so I really recommend put your gravity system at the front, because your lateral restraints and all of that sort of thing. Rob Jury said a little while ago, really all of the lateral system is there to keep your gravity system intact, and it sort of stuck with me. So the gravity system stops things falling on our heads. So put in your beam layout plan, or how your gravity system is going to be working, and then pretty clearly try to just mark it out, so that when people are going through the beams and so on, they can easily reference across. If your checker can do that, then they can say, okay, well, that makes sense, that makes sense, that makes sense. And if you're looking at it and you can say, okay, well, that's going to need a steel beam there, is that there? That's great. If people have to look through it a lot more, then you're more likely to be getting an RFI. A lot of the questions that they were getting were, please explain this, please explain that. If you set it out with the picture, it's just nice and easy. And then you can cross-reference it across. This engineer on this particular job had put in a beam summary at the front. I'd never seen that before, but I thought that it was really good. And so I just included it in this. And there he put in, deflection okay, strength okay for each one of the beams that he'd designed. And then just, as I say, beam one's a 200 UB 22, and you can look back at the back at the beam layout plan for that. Then with your lateral, so he'd done some jib bracing, and there was a portal frame over the garage. Now, one thing I highly recommend is if you just do the calculations, then it's actually really hard to check at a glance. And if you looked at Stanley's presentation yesterday, then for these types of houses and so on, they don't get a lot of time, to be able to go through and have a good look. And so if you can just mark out what's the tributary area that you're assigning to your portal frame, then it just makes it a lot easier, and you go, oh, yeah, that looks about right. So, you've got a flexible diaphragm, or you're assuming a rigid diaphragm, or whatever else it may be. Angela Liu's work says that in residential, then, you should be looking at a fairly rigid diaphragm. When I was a real engineer, then we used to assume that the diaphragms were reasonably flexible, but it turns out that that is incorrect. And so, what's your tributary area? And then just a picture of the portal. What are the NET detailing? How are you holding it down? It doesn't take up much. This is just an A4 page, but you can just pop it in there. And then once again with the calculations. Now, this probably won't meet, ironically, the work that I did to put out the portal frame design guide, but nevertheless, that's the calculations. He's put it in there, he's shown his assumptions, and it makes it nice and clear and easy. Same with the foundations. All that we're doing, exactly as Paul Campbell was saying yesterday, and has been backed up by, I think, just about every lecture since. Load path, load path, load path. Start at the top and follow it down. One of the things is that we, as engineers, we start to design at the top typically and get our loads and then put it down into the foundations. Builders build the other way, of course. And so one of the problems that we did see with the drawings, different slide, sorry, with the drawings was that, some of them were quite difficult to read. And so try to draw your stuff in the way that the builder's going to be building it. The builder's not going to be building your beams first or your roof bracing, so don't put them at the front. He's going to be starting with probably your retaining walls and your foundation system. So put those at the front so that they know what's going on. And with your construction monitoring, highly, highly recommend just make a note on there saying refer construction monitoring schedule, just in case it doesn't get through to them. Typically, as you know, you walk onto site and they might have your drawings there, but maybe the architect hasn't sent it through or the construction monitoring schedule. So you need to make sure that that's referenced in there. But yeah, and so what are the assumptions that you're making with garage foundations and so on? And then a ground assessment. So, whereabouts is the data that you're getting it from, whether it's a geotech report, whether you've got, gone out and done a few scalers, whatever else it may be. I suspect that there's going to be less people doing ground testing after Ian's story in the last session. And but basically what it does, right, is it's talking about a clear story. If we can, if we can just be telling a clear story right from the drawings that we're putting down through to the calculations that we're getting across. The best work that we've seen didn't get it. And one of the, Stephen Sowery in the room? Yep, brilliant. So one of the jobs that I saw was actually Stephen Sowery's from Sowery Consulting Engineers down in Lower Hutt. I'm a big believer in calling out good work when I see it. And there was a series of townhouses that he did for I was about to say for a developer, and it was all just nicely set out, right? There were almost no RFIs that came back to it. The construction monitoring schedules and so on were there, went out and did the construction monitoring, and it was all just a really nice, tight package. And maybe he'd be happy to show it afterwards. I don't know. He's just at the back there. Feel free to hit him up at lunchtime. And yeah, that's just about me. Has anybody got any questions? I've got 7 minutes of standing up here in nervous anticipation.
Thank you, Martin. Anyone got any questions?
So you showed there the certificate of design work.
Yep.
Which they often ask for as well as the PS1.
Yes.
And it just seems like a whole lot more paperwork for the same information.
Yeah, it's the certificate of design work is because when you're CPEng, you are deemed to comply as an LBP3, right? And so for residential work, it must be done by a licensed building practitioner, designed and built. That's why you don't have to fill one in for commercial work, right? And buildings over, I think, 11 metres high, 10 metres high, somewhere in there. And so, yeah, you do have to fill one in for that. As I say, you know, the duplication, so on the system that I've got coming up, I'm trying to eliminate as much of that as possible so that, you know, if you make a bit of a mistake on, you know, your address is wrong or something along those lines, I've done it, I'm sure that most of us have here, then it doesn't come back as an RFI and bite you. Or if it does, then it's duplicated all the way through your paperwork. Sorry.
I had a question for you, Martin. With your templates, is that going to include a template part only attachment? So where engineers tick part only as per attached and then don't actually attach to describe the work that was being designed or work covered under the PS1? Will there be included a template for that?
For the part, sorry, say that one again?
On the PS1 where we tick part only of the work, so we
Yep.
haven't designed all the work but just part only,
Yep.
and it says refer attachment.
Oh, right, okay, gotcha. So on there, what I'm doing is I'm giving examples, right? And so you would be saying, on your PS1, for example, SED beams as per beam layout plan.
Yeah.
You know, SED foundations as per foundation or whatever else it may be, bracing plan. And so it makes it nice and easy, and it also encourages people to be putting in the beam layout plan, for example.
Martin, what was your letter in lieu? What was that referring to?
The letter in lieu is, you can download it from the website. There. And so, come to my next talk at the ACA. But basically what we've got is that with durability, then we have a clear compliance pathways for most of our work through the standards that we use, right? And so the letter in lieu, if you read the design guide that's on the Engineering New Zealand website, where you download the producer statements from, or the durability guidelines, sorry, they were produced by Adam Thornton, Craig Lewis had a hand in it, as did Ray Elserath and so on. And so those have been accepted by BCAs throughout the country. And the letter in lieu is just saying, you know, how you've designed and got it to comply with B2 and thereby B1.
It's in lieu
A
of
PS1.
putting B2 on your PS1.
Yeah.
That's very succinct, thank you.
The Auckland Council produces a document says if you produce your own drawings, you don't have to sign the architect's drawings. So my firm for the last 20-something years has always been producing our own structural drawings. We don't photocopy anything from the architect and we don't sign any of the architect's drawings, and we've never been asked.
Seems like a good idea.
If we could all thank Martin for his talk.
Thank you.
Okay, our last talk for this session is Nick Clendon. Nick Clendon has 17 years' experience as an engineering geologist, gained both here in New Zealand and abroad, and is currently based in Wellington, where he leads the local Tetra Tech Coffey team. Nick has worked on a range of projects and has been involved in roading investigations, design of transmission towers and pole foundations, new build supermarkets, commercial buildings, design, inspection and review of deep pile foundations, including IL3 and IL4 structures, such as hospitals, pump stations and new school buildings. Thank you, Nick.
So my talk's really around B1, VM4 around the shallow foundations. I come from I'm an engineering geologist, so this might be a little bit of a different approach to what you guys are used to. I started the project hoping I'd get a bunch of good data from insurance companies or MBIE around about how B1, VM4 has performed, as in how many settlement-related issues we might have, how many buildings out of 10 actually suffer issues, how many buildings are we repairing. But when I started the process, I got good responses from all the insurance councils. They were quite clear that no, they don't keep any of that data. Which was a little disappointing. I'm not sure whether that's the total truth or not, but at least pushed me in a slightly different direction. So what I'm really presenting is kind of some of the key things that I see happen from an engineering geologist point of view in terms of when we get involved in things I guess maybe have gone wrong and why they might have gone wrong. Just a list of bits we'll jump through, but we'll just get started. Bearing capacity, as we know, is provided in B1 VM4. There's some perfectly normal bearing capacity calcs. We also talk about it in terms of good ground and using a bearing capacity of 300, which can be a little misleading, and we also cover it again in the NZGS modules. So the NZGS modules are a bit more of an update from a geotech perspective. Sometimes there's not necessarily good terminology shared between the different standards, which can lead to a little bit of confusion. You've got to think bearing capacity failures itself are extremely rare. I don't know if I've ever seen one in my career. Seen lots of excessive settlement occur, but we very rarely actually ever get to the point of having bearing capacity failure. It's quite hard. So, to get an actual bearing capacity failure, you're looking at gross rupture, 15 to 30% of your foundation. Even for a reasonably small strip footing, that might be 75 or 100 mils or more. So you'd normally be really concerned well before it gets to that point. There's a definition in good ground in 3604 we use a lot. It's not really related to bearing capacity. I think over time it's shifted a little bit. Traditionally it was connected to bearing capacity and bearing capacity calculations, but as we've increased that DCP count that we use to assess it, really what we've done is we've kind of used it as more of a limiting bearing capacity. So we're really using, I guess, bearing capacity theories to provide us with an estimate of settlement. Not sure if that's what we intended when it started out, but that's where it ended up. I think it would be, in a way, good to separate out the bearing capacity of good ground as being more of a limiting bearing capacity or an elastic bearing capacity. So when you provide that bearing capacity, or if I provide it to a structural and I said this is what it's for, I'm telling the structure he doesn't need to do a settlement calculation. If I provided you with an ultimate bearing capacity, my expectation would be that you'd be doing a settlement assessment at some point. And they're two quite different things. There's no guidance on settlement in B1 VM4. It's just an empty section at the moment, so one day it'll get filled in. There's some acceptability criteria, which we know, which is 1 in 240, which is useful, but may need updating. And just as an idea, if we look back at where we started from, used to go for 3 blows per 100 mils, would give you traditionally in, say, sand soils around 300 kPa bearing capacity. These days, if you actually tested that, 5 blows would be more like around 50, and we've actually kind of just turned that down to 300. So really, we've kind of reduced our bearing capacity by, say, 50%-ish. It's how we've kind of managed stuff. Just to look at fine grain soils, so on that chart there, that 20 is around about 5 blows per 100 mils. This is millimetres per blow, and you can see kind of the relationship between millimetres per blow and undulating shear strength. Now, these probably change depending on your soil types. I think these samples are from Iraq somewhere. But as an idea, if you actually got 5 blows per 100 on a clay soil at a given moisture, you might be looking at a bearing capacity of 500 plus kPa on a half metre wide strip footing, which is quite a lot higher but you might be a bit concerned about your settlement performance if you did that. Again, moisture content relating to blows, millimetres per blow. And what you can see here, it's interesting, is you get a reduction of about, say, 10% of moisture. You're about halving your, well, I should say you're doubling your blow count, really. So maybe it's going from, I don't know, 5 blows per 100 up to kind of half of that or double. But either way, you're halving or doubling your blow count with about a 10% change in moisture, in theory, in natural ground conditions. There's a big relationship between moisture content and shear strength. So some of these will give you a background. You know, the relationship arrives that actually, as you get to the liquid limit of a soil, and it's basically collapsing and turn into a fluid, your kPa is down at 1.7. When you're at the plastic, which is when it kind of rolls a nice thread and is a bit malleable, you're up at about 170 kPa. If you go beyond that, so if you go on this chart out here to the left, you get into the brittle, crumbly type soils, which is probably more concerning. If you go out here, it's pretty obvious it's no good because you'll sink into it. What catches people out is probably more this side of the chart. It looks like that side of the chart should be good, but it can be a bit misleading. What we find is brittle and crumbly type soils are often logged incorrectly and can give you quite misleading strength values. So this is an example here from fill material. So this is taken in Wellington. It's a moderately plastic silt, some clay in it. The first line you want to look at is a blue one, which is our compaction curve. So this is a remoulded sample. And we compacted at different moisture contents, each of the dots, using the same methodology, and you get a density or dry density. And from this, we can work out a 95% compaction, which is what we use when placing fill. The orange line is interesting, is you get really good shear strengths out here on the dry end. As soon as your moisture starts to increase too much, not only does your dry density drop, but your shear values plummet. So here you're looking at going from over 200 kPa shear strength. With about 4 or 5% increase in moisture, you're down at 50 kPa or potentially less. So it's a huge drop at a relatively small change in moisture content. This side is quite good though. This is great. You turn up the site. If you saw this, you test it with a DCP or shear vane, you'd get a bad result. Happy days, you tell the guys they've done a bad job. This side out here is actually a bit misleading. So what happens is it gets drier, is things like DCP results, as we saw, and shear vanes tend to perform really well. You'll get very high values. But it's really just a function of the soil being dry and hard, not actually of the soil actually having good strength. And so what I've seen mostly with fills is where they've been tested and had good DCP results, and 6 months later when they've got wet, they've actually turned very soft. And then you find the DCP results go from being over 5 to down at 1 and 2s. Catches people out. I guess if the soil moisture has such a high impact, how do we collect the data to make sure we're comfortable with what we're actually getting from our data? Soil logging is really important. Good, clear descriptions of the soils. You can't do DCPs without a soil log. The data doesn't work. It doesn't actually have any application. Moisture content's important. If you're getting logs from a geotech and it's showing dry, dry, dry all the way down to 2 metres, it should be ringing alarm bells that the scalar results and shear vanes might be wrong. You know, you should be able to roll a thread on site. If the soils are brittle and crumbly and you can't roll the material, it's probably dry and it's probably giving you misleading results. And if it's dry, it often has the ability to absorb more moisture, which can either make it soft and settle or in some cases expansive and swell up. Adabug testing and classification testing is really good. If you're not sure, send it off, get a moisture content. If the moisture content's way below your plastic limit, you're dry and crumbly. You want to be around your plastic limit or even a bit higher. Then you know that at least your shear vanes and DCPs are probably giving you indicative strengths. Also understand your moisture history. If you're working locally, you know what the weather's been like. If it's been really dry for 2 months, maybe it's not a great time to go out and do your testing. If you've gone up to Hawke's Bay to do some testing and it's been dry there, you should at least ask the local contractors what the weather's been like and get an understanding of it. So as an idea of how much that moisture can change, this is in Manureya in Auckland, the same site. So, you know, even down at 1.5 metres in the same location, we're getting like a 15% change in moisture. near the surface it's over 20%. So these are big moisture changes. And these can have a huge impact on your results. In this case, it's natural soils, which can be quite different from fill or remoulded soils. But this would have a big impact on your expansive soils. So just understanding, just summary of kind of the soils. Your test data informs your bearing capacity, but if your data hasn't been collected right or you don't understand how your data has been collected, there's a good chance you're just going to get your bearing capacity assessments wrong. You'll have good DCP results, you assume a good bearing capacity, it rains in the winter, actually you haven't got what you thought. You can easily get a 10% change in moisture, we saw that on the last graph, and this can relate to dropping your blows from 10 to 4. So 10 blows on a DCP is great, happy days. Once it's down to 4, it's actually no good anymore. So you do need to be careful about it. I think one of the things I'd like to see is that definition good ground gets changed a little bit, so it's differentiated from the bearing capacity and the bearing capacity calculations. This is so that it's clear is that when someone's providing you this good ground or this limiting bearing capacity, that it's quite different from a traditional bearing capacity calculation, and not to be confused. The acceptable settlement criteria, which is listed or stated in B1 VM4, is 1 in 240 or 25 mils over 6 metres for serviceability. There's nothing provided on ultimate limit state, which is probably sensible because it's quite dependent on the building types and the structures. But a lot of modern houses, like if you go in Wellington to an old house, especially for your old timber frame and timber pile houses, you'd get way more than 25 mils across that house. And to be honest, you get 25 mils across some rooms. It's actually generally reasonably well accepted. People expect their windows not to open on an old villa. They expect the doors to bang a bit in the wind. I think in modern houses, if you're paying $500,000 or $1 million for a new build house, you'd probably be a bit disappointed with that performance. Most houses I'm seeing that generally meet the expectation of more like 1 in 500. I just think that criteria could be worth reviewing and seeing how it fits with modern buildings. And this is really around the construction of modern buildings with concrete floors, especially when you get architects doing polished floors, which some people like. But if they get cracks in it, nobody's super impressed with that, even if they are just small cracks. And also insulation, minimising gaps, drafts, windows and doors opening and how they're all built. So it's probably a good time to review it if we do actually start to look at B1 VM4. One of the things I did want to say is there is some really simple solutions for doing settlement assessments. I know it's not captured in B1 VM4, but if you guys are doing stuff and you're a little concerned about it, especially at serviceability, there is some really simple stuff you can do, just using Young's modulus. So this equation here, you have to do a very complex rearrangement of that by shifting the B over to the other side, and then things will work. But it's very easy once you've done some scalars, and the NZGS module gives you descriptions of soils against your DCP results, and as you can see, you can just simply pick off a Young's modulus value. And they're fairly robust. It's actually quite hard to get those Young's modulus values horribly wrong, as long as you understand the soil conditions when you've done your testing and your data. So it's a reasonably simple calculation to do. The only bit you need to check is this IG, which is like an influence factor for the shape and the size of your foundation. But the rest is pretty basic. And it gives you an easy tool for estimating. And this is one of those influence charts, so you can literally calculate it off here. This graph here, don't overthink it too much. I hope I won't ever see any structural engineers produce something like this. I'd be horrified. I'd be horrified at myself if I produced it and gave it to somebody. But I really did it to highlight some key issues that we have. So these are actually done on very large pad foundations, 2.5. And as you'll notice, as you go from small foundations to bigger foundations, bearing capacity becomes less of an issue and settlement becomes much more critical. Once you're over anything of about 2 metres in terms of dimensions, bearing capacity is almost a kind of a moot point actually, and it's almost near impossible to get a bearing failure, but settlement is going to be a significant issue. The key things in this to see is this dotted line here is really what our settlement bearing capacity might be on the basis that you're actually testing it correctly to that 5 blows and taking the actual strength of the soils. What we've done artificially by screwing down, I guess, by increasing the DCP count from that 3 to 5 and actually reducing the bearing capacity, is we're actually back on this line here. So we've kind of artificially, by introducing that increase in the bearing or the DCP count, is we've actually kind of reduced our sediment by a factor roughly of 2. It's just for your knowledge. I think the reason this is important is the original testing of around 3 blows per 100 mils was probably technically correct for bearing capacity, and if everything was okay, produced about the right level of settlement. But it kind of ignored the classic geotechnical fudge factor of 1/2 and 2, as in if you have any variability on your site, you're quite exposed to getting excessive settlement. If you go from 25 mils and you double it, you're at 50 over here, and you could be at 10 or 12 over here, and suddenly you've got 30 plus mils of settlement. So this factor of 2, in theory, should have helped reduce some of those issues. I guess, again, we don't really know without kind of going back through some historical data. And the other one is the coarse-grained material, the blue line. The big thing to note there is that actually settlement is significantly less of a concern on coarse-grained material. So if you definitely are in sands and gravels, excluding things like liquefaction, generally sands and gravels are pretty good when it comes to just your static settlement and serviceability. But generally, if you're doing these sort of simple calcs, if you've got anything over 15 mils in your serviceability condition of settlement you're calculating, you should start to think about that, because that's probably more than what you want to see, and probably start to think a bit more details about it. One last note is ignore anything after about 50 mils. So these calculations are only really good to about 25 or 50 mils of settlement. After that, the rest of the information is probably pretty rubbish. They're designed on the basis of reasonably well-designed foundations in reasonably okay conditions. So buildings are expected to perform okay. So they're applicable for that kind of 0 to 25 or 0 to 50 mils max, and beyond that, the settlement calculations aren't very precise using this method, and you need to go do something more. So, yeah, just conclusions. The big thing is actually small percent changes in moisture and fill material can make a huge difference to your strength. 2 to 3% change, especially at that critical junction when you're getting near to your air voids, can really plummet your shear strength. So a lot of the issues I see in Wellington are tied with fill materials. It's often tied to fill materials that haven't been compacted at the right moisture content to minimise air voids. If you compact the soils at too low a moisture content, you get too much air voids, and it works like a sponge. It'll suck the moisture in, and you'll see it on site. It's all bouncy and soft. Natural soils can vary heaps, 5 to 20%. It's a bit harder to quantify the impact of this. Depends on the soil type and the climate and fines gradings, but you definitely want to be thinking about expensive soils, especially when you're in Auckland and north of Auckland. It's a big issue. You need to be careful about the time of year you do your testing and taking your classification tests. Settlement on coarse-grained soils, sands, etc., is a lot less than fine grains. So there's a big difference between doing a DCP in sands and getting, say, 2 or 3 blows in sand. That's actually probably not going to be a big settlement issue. Getting 2 or 3 blows in clays and soft soils and fine grains may or may not be a settlement issue. We've kind of used DCP and increasing the DCP value as a way of managing, I guess, our risk in it. I don't think we've gone back in time and looked at how well B1, BM4 has performed, and something maybe I need to talk to some of the local BCAs about. I guess the risk I see is that we increase the DCP to deal with issues like liquefaction or settlement problems that we've had. All we're doing is creating a circumstance where we're going to be very conservative in some areas, such as gravels and sands, and in other areas we might not be addressing the underlying cause of the problems. Yeah, and going forward, really, the next step, I think, if we're going to make any changes to B1, BM4, is really going back and looking at historical data and how well B1, BM4 has actually performed for us. So what I don't know is really how many settlement-related issues we're getting from with our building industry, and whether that's an acceptable number or not. Having to re-level one building in 1,000 or one building in 10,000, I guess, is that worth the cost or not? So something to think about. Thank you.
Thank you, Nick. That was very interesting. Any questions? So, Nick, we've got time for a few questions. No. Yeah. PJ.
Thank you, Nick. That was very interesting, actually. we were reading section C4, which is the geotech part of the assessment code, and it talks about yield in soils, which puzzles me. Because if you're getting a very highly stressed piece of soil under a rocking foundation, for example, it can't really yield, can it? Because it just changes the pressure bulb. Can you explain what's happening there?
It really...
We're talking about soil structure interaction.
Yeah, so in these calculations we're using what we call the elastic modulus. This is totally on the assumption that the soil somehow is going to rebound 100%. It never really does that unless you're talking about really, really low strains. So we're talking maybe within a 1 or 2 mils, and if you took the load off, it might bounce back. But very early on in soils, you start to get permanent plastic deformation. It wouldn't quite be as sharp as what you see in steel or concrete yielding, I guess, but it's more gradual. So right from the start of the curve, you start to develop plastic, and it just keeps on deforming as you put more stress on it. So the more stress you apply to the soil, the softer it becomes, and the more displacement you get, and the less that will rebound back. So if you did actually put, I don't know, whatever, 100 kPa on a soil and displaced 100 millimetres, and then you took that load off or something, it might come back 5 mils or 10 mils at the most, but it'll be a very small amount. Essentially, it's plastic deformation. If that makes sense.
Any other questions? I had a question just with all the uncertainty and what you've just outlined. What's your thoughts on engineers, structural engineers cracking out the soil testing gear and doing penetrometer tests? I mean, personally, I worked previously in Australia, and at the moment over there, they do not even do residential without geotech involvement, so I was just curious on your comments.
Yeah, look, I know some people in the past have rubbished things like the DCPs and say they shouldn't be used. I think it's a perfectly good tool if used appropriately. I think it's no different to your ETAB software you run, as in if you use it badly, it's going to give you rubbish answers. So it's kind of just user beware. I think, structural engineers who work in that space and use it regularly, as long as they're aware of those risks and how to collect the data. And again, I think it's acting within their competency. But I guess the key thing is being aware that in the top 2-3 metres of soil, things like that weather over the last week or two can play a big part in the results you get. So that's good.
Any other questions?
Yeah, I've still got my shear vane, by the way. I check footings and things. But my question for you, Nick, is the position between this conversation between the structural engineer and the geotech engineer. And sometimes as a structural engineer, I push back to the geotech and say, I need more information from you. A lot of what you've explained today is over my head, to be honest, but I would expect the geotech to provide me with the kind of information that you're talking about. Is that reasonable, or is it up to the structural engineer to actually do this sort of work?
No, we should be providing what the structural engineers to do his job. So the reason for me being here is understanding, I guess, what's important to structural engineers and what's actually going to make a difference. I think a lot of the soil stuff and ground-based stuff, it's really more relevant when we talk about resilience, low damage design. I think we have less of an impact when it comes to life safety and collapse of buildings, but I think there's been a big topic about damage reduction, and then a small amount of settlement can play a big part in that. So I think it's you communicating to, I guess, the geotechnical engineer you're working with exactly what it is that's important to you, and then putting it in a suitable, I guess, shape and form for you to actually utilise. And that can be done a lot of ways, I guess, is a problem. So there's probably no right answer to that. I think it does come to have this conversation. So when I went to the NZGS conference at the start of the year, there was lots of comments about structural engineers, and we see structural engineers the same you guys see architects. So probably made no friends, but but better, not as bad architects. But it's that same level of communication we need. I think that it's important we actually do have that time. And it has been way better over the last 10 years than what it has been the previous 10 before that. So there's been heaps of improvements. And on the whole, I know the people I get to work with, you generally just ask that question is actually how do you want it and what format you want it in and where is it important to you guys. So I guess it's something you need to convey what's really important to you, and then that way to make sure you get back what you want from them correctly. So, yeah.
Last, anyone got one more quick one? Last one.
As a reviewer, I've had a lot of arguments with engineers who want to design on 1 or 2 blows per 100 on that Scala test by reducing the bearing pressures that they're calculating down to 50 or whatever, 30 kPa. And they always just point to B1, VM4 and say, oh, I've applied a 50% reduction factor to my Scala of 2, which gave me a bearing capacity of 200, so it's all good. What kind of framework can we have to push back and get a little bit of sensibility there from a geotech point of view? Like, what argument can I deploy to say, I don't think this is right, and here's a really convincing geotech-sounding explanation of why?
A settlement assessment. I mean, when you're screwing down that bearing capacity providing, you're doing it to reduce the settlement. So if you think they're kind of fudging numbers, then I'd be saying, please provide a settlement calculation. So they need the loads from the structural at whatever load combinations is appropriate, and they need to do a settlement assessment. That's what I'd be. As soon as people are going under 300 kPa, maybe down to 200 is okay. But if you've seen stuff where people are giving you bearing capacity down to 200 kPa, you should be starting to get alarmed about settlement. That would be my advice.
Thank you very much. And join me in thanking all of our presenters from this session.